Dear students, in today's session we will be discussing two-stack PDA. Okay, we'll start our discussion with the FA. In FA, we know that we have only a finite state control, okay, which is attached with an input. Okay, so only with the change of the states we remember something. So in this manner, our FA works, and our FA is able to recognize only the regular languages, nothing else. Okay. Then we have added one, suppose PDS, push down store to our finite state system. Then it becomes a PDA. Okay. And we have already seen that our FA were not able to recognize the languages of the form A to the power n, B to the power n. Means the languages where we have to match two quantities. So it was not possible in case of FAs, but PDAs were able to do it because of the presence of this additional memory in the form of a stack, by which we can push something and then we can pop something. So with the help of this stack, we were able to perform matching. So our PDA was able to represent the languages where we should match two quantities. From the discussion of our previous sessions, it is very much clear that PDA is able to represent the regular languages as well as context-free languages, including the languages of the form where we have to match two quantities. But suppose our language is L is equal to A to the power n, B to the power n, C to the power n greater than equal to 1. In this language, if you look at, we have to match not two but the three quantities. Is it possible to write a PDA corresponding to it? At this point of time, I will request you that you pause your video for 2 minutes and just try to think the strategy by which you can write the PDA for such languages. Is it possible or not? This we have to check. Up till now, you would have been understood that it is not possible to write a PDA for this particular language where we have to match three quantities. Why? Because suppose I want to write a PDA for it. How I will be writing, I have to first decide its strategy. Its strategy may be, I will be first pushing A's because I have to match the number of A's and number of B's. So I will be pushing all the A's over the push down store. Then when I will start getting B's, I will match them with the A's. When all A's will finish from the push down store, all B's will be matched. But then what about C's? How I will ensure that equal number of C's should also be present in the language? Okay, so this third quantity we are not able to match if we are trying to write a PDA corresponding to it. Now come to another strategy, to our next machine model, that is a two-stack PDA model, in which we add one more stack. So rather than having a single stack as was the case for our normal push down automata, we are having one more PDS. So this is PDS1 and this is PDS2. So this will have two memories in the form of the stack. Whether this machine model will be more powerful or not. Yes, this machine model will be more powerful. It will be able to recognize all the regular languages, all the context-free languages, including the languages where we have to match two quantities. Even it will be able to recognize all the language. It will be able to represent all the languages where we have to match more than two quantities, like the language is A to the power n, B to the power n, C to the power n greater than equal to 1. So in this manner, by adding this memory, this additional stack, it adds power to this machine. So it will become a more powerful machine. As we have seen that the problem where the number of A's, B's and C's are equal, that is AN, BN, CN, and greater than equal to 1, cannot be solved using the normal PDA. Okay. So now we'll try to solve this problem using the two-stack PDA. And as we have done for the PDA also, we will first try to chalk out its strategy. Its strategy will be when all A's will come to us, we will push all these A's over both the push down store. Because it is a two-stack PDA, so we are having two memories attached with our machine, that is the two push down stores, PDS1 and PDS2 we will be saying. So we will push A's on both the PDS, and when we will be start getting B's in our input, corresponding to each B, we will match it with the A's stored over one of the PDS. Okay, so at one of the PDS we will be matching it, and the other PDS we will keep as it is. When C will come, then we will match it with the A's stored over the second PDAs. Okay, so in this manner we can match A's with the B's as well as A's with the C's, and we will ensure that the number of A's and number of B's are equal, and number of A's and number of C's are also equal. So in this manner we will be ensuring it. So now, as per this strategy, I will be writing my transitions. So let us start with the start state, that is the Q0. Initially, I will get an A in the input, and at the top of the push down store, because now we are having two push down stores, so we have two push down store symbols. So we assume that Z0 is the initial push down store symbol over the PDS1, and Z0 dash is the initial push down store symbol on the PDS2. Okay, so this will be the initial situation. In this situation, because we are getting the first A, what we have to do with this A, we have to push it over both the push down stores. So that's why I will not change the state. I will remain in the state Q0, and I will push this A over the first push down store. So I will write A Z0. So I will maintain Z0 over the push down store 1, and then also push an A there. Similar in the situation with the PDS2, I will maintain the status of the PDS2 by writing Z0 dash, and then I will be pushing an A also. So that's why I will be writing AZ0 dash. So now A is on the top of both the push down stores. Okay. So now next situation will be, we are at the Q0 state itself. Over the top of the both the push down store, there will be an A, because we have pushed A over both the push down stores. And then in the input also we will be getting an A. What we have to do, this second A also we have to push over both the push down stores. So that's why we will remain in the state Q0, and we will be writing AA and AA on both the push down store. So this 1A for keeping the status of keeping the topmost A as it is, and the second A which we are pushing from the input. So this is the situation for both the push down store. So through these two transitions, we will be pushing our A's which we are getting in the input over both the push down stores. Okay, so now both the push down stores has the A's which we were getting in the inputs. Now we will start receiving our B's. When we start receiving B's, we have to match it with the A's. So we have A's stored over two push down stores. So one push down store we will keep as it is, and other push down store we will start matching with B's. Okay, so let us assume that PDS1 we are matching with B's, and the PDS2 we will keep its status as it is. Okay, so we are getting first B, so we are writing null over the first PDS so that topmost symbol A is erased, and we are writing A on the PDS2 so that its status may be maintained. And as we have changed the operation from pushing, we have come to the matching, so that's why we have changed our state to the Q1. So now we are in the state Q1 and receiving other B's. So in the Q1 state we will receive other B's, and at the top of the push down stores there will be A. Okay, so topmost symbol A from the first PDS has been erased, but there may be other A's as well. Okay, because we are getting B's, so it has to be matched. Now again we will be writing null to the PDS1 and A to the PDS2 so that the status of the PDS2 will be maintained, and topmost symbol A present on the PDS1 will be erased. So the second B will also be matched, and we will remain in the Q1 state. So all other B's we will also be getting in the similar situation. That is, we are in the Q1 state getting B's, and on the top of both the push down stores there is a symbol A. Okay, so in this manner we will match all our B's. We will match all our B's. Now when we match all our B's, and if the number of B's are exactly equal to the number of A's, so whatsoever A's we have pushed over the PDS1, those all A's will be popped up, because the number of A's are exactly equal to the number of B's. So when B's are finished, all A's from the PDS1 will vanish, will be popped out, will be erased. So now on the PDS1 there will be remaining the symbol Z0, which was the initial push down store symbol, while on the PDS2 we will be having all A's stored as it is. Okay, so now if such a situation is there, so we will be in the Q1 state receiving our first C. On the top of push down store will be the Z0, and then on the top of push down PDS2 will be the symbol A. In such situation, now we will start matching these C's with the A's present on the PDS2. So what we have to do for this matching, we have to write null to the PDS2. So that The same thing we are doing here. We have changed our state Q2 because now we started erasing. Still we are erasing, but we started erasing from the second PDA. So that's why we have changed the state. If you do not change the state, then also we can write the PDA, because at least one change either to the PDS1 or to the PDS2 or to the state is required to identify the change. Okay, so but it is general guideline. It will be easier for us if we change the state, if we follow the guideline. Whenever we change the operation, or we will or we do something different, then we will be changing the state. Okay, so we will move to the Q2 state and we will write null to the PDS2, so that the A which is stored as the topmost symbol on the PDS2 will be matched with this C, and we will maintain the status of this PDS1, that is the Z0. We will not erase it, because if we erase this Z0 as well, our PDS1 will become empty and our machine will halt. So that we don't have to do right at this point of time, because we are still to ensure that number of C's and number of A's are equal. So through this transition, we have matched our first C with the A present on the top of the PDS2. Okay. Now we are in the Q2 state. We are getting other C's. Okay. So we will be getting C's on the top of the PDS1 will be the Z0, but on the top of PDS2 will be the A again. Again, we have to match it, this C with this A. So we will write a null here. We will maintain the status of the PDS1, that is, we will write Z0 here, and we will remain in the Q2 state. So all other C's which we will be getting from the input, we will be getting in the Q2 state, and using this particular transition, we will match all the C's with the A's present on the PDS2. Okay. If again, number of A's and number of C's are equal, so when our C's in the input will finish, all A's from the PDS2 will be erased, will be popped up. So on only symbol remained on the PDS2 will be the Z0 dash. Meaning thereby we will reach to a situation when we are in the Q2 state. At the top of the push down store 1, there is the symbol Z0. At the top of the push down store 2, there is the symbol Z0 dash, and our input has exhausted. Okay, so we can take only the null move. We can take only null from the input. So Q2 null Z0, Z0 dash will be the situation, and this is the situation in which we have to signal the success. So we will signal the success by making both the push down stores empty. So we will remove Z0 and Z0 dash. So that's why we have written null and null here, and we have remained in the Q2 state. So because our push down stores are empty, so our string will be accepted. So in this manner, we can get such strings where the number of A's, number of B's, and number of C's are simultaneously equal through this two-stack PDA. So this is the solution. Now let us come to the next problem, which is closely related to the previous problem. The problem is a to the power n, b to the power n, c to the power n, d to the power n, n greater than equal to 1. Here we have to match 4 quantities simultaneously. In last example, we have matched 3 quantities simultaneously with the help of 2 push down stores. Now here we have to match 4 quantities. If we take the previous study, suppose we are having a 2-stack PDA. Okay, so we can match only the 3 quantities. Why? Because when A's will come, we will push over both the push down stores, and we will match B's with the A's stored on the PDS1, and C's we will match with the A's stored on the PDS2. How do we match D's? Or suppose we are having not 4 but the 5 quantities to be matched, or 6 quantities to be matched. So corresponding to each such language, do we need to add one more stack? Is it necessary? No, it is not. So we will have some other technique by which we will be representing this particular language with the help of 2 stacks only. And even if we have to match more quantities, suppose 5, 6, 7 or any number of quantities, we will be able to match with the help of only the 2 stacks. So meaning thereby adding more than 2 stacks will not add power to the machine. Okay, it may make your design easier, but it will not add power to the machine. So only with the help of 2 stacks, we will be able to match any number of quantities. So it will be the equally powerful machine as a 3-stack PDA or the 4-stack PDA or the 5-stack PDA. So that's why 2-stack PDAs are important. We need not to add more stacks. Let us see how we can do it. let us assume we are having two stacks, one with the symbol Z0 and another with the initial push down store symbol Z0 dash. Now suppose we have to represent or we have to test this a word from this language. So in starting we'll start getting A's. So what we'll do, suppose there are three number of A's. I am taking an example. Suppose the value of n is equal to 3. So what I will do, I will add these A's or push these A's on the stack 1. Suppose this is my PDS 1. This is my PDS 2. So when I will read the first A, I will push it. I will not push it. I will maintain the status of the PDS 2. Okay, I will not push it here. I will push only on the PDS 1. Then I will be reading the second A. Then I will be pushing it over the PDS 1 and maintaining the status of the PDS 2. Then similarly, when next A comes, I will push it on the PDS 1 and maintain the status of the PDS 2. Meaning thereby, I will push all the A's over the PDS 1 only. Okay. Then I will start reading B's in my input. Again, if my word is belongs to this language, so word will be something like this: triple A, triple B, triple C, and triple D, something like this. So now I have started reading B's. So when I will read B's, I will match it with the A's stored over the PDS 1. And when I will be matching, so meaning thereby I will be removing the topmost A from the PDS 1. And when I will remove the topmost A from the PDS 1, at the same time, I will push that A on the PDS 2. Means I will remove A from the PDS 1 and I will push that A to the PDS 2. So in this manner, whatsoever I am deleting, I am keeping the track of that through the PDS 2. So let us do it. Suppose first B has come. So I will remove the topmost A from the PDS 1 and I will add an A to the PDS 2. I will push an A to the PDS 2. So these two work I will be doing simultaneously. Now when the second B comes, I will remove one more A from here and I will push one more A on the PDS 2. Then I will be reading the third B. I will be removing this A and I will be pushing one more A here. So now, because the number of B's and number of A's are exactly equal, so I have removed all the A's from the PDS 1, but all those A's are now present on the PDS 2. So I have not lost that quantity. I have not lost that quantity. So now it is available there. So when I will start getting C's. Now this time I will match these C's with the A's present on the PDS 2. Okay. Again, because I have to match one more quantity, so what I will do, I will remove A's from here. So corresponding to each C, I will remove an A from here and I will be adding an A to the PDS 1. So start doing this. I will get first C, I will remove this A and push it on the PDS 1. Now I will get the second C. So I will remove one A from the PDS 2 and push one A over the PDS 1. Now I will get the third C. I will remove one A from the PDS 2 and add or push one A on the PDS 1. So I have successfully matched the C's also with the A's. And if the number of C's and number of A's are equal, so when I will start reading D's, my PDS 2 will not be having any A's present over it. It will be having Z0 dash. Okay. So now when I will start reading D's, so simply what I have to do, I have to maintain the status of the PDS 2 because no more quantity has to be matched. So simply I have to match this D with the A's present on the PDS 1. Nothing has to be pushed over the PDS 2. Okay. So when I am reading D's, that is the last quantity to be matched. So corresponding to each D, I will remove one A from the PDS 1. So I will read first D, I will remove an A from the PDS 1. Then I will take the second D and I will remove one more A from the PDS. Then I will take the third one and I will remove the next A from the PDS. And if the number of D's are also equal to the number of A's, so we will reach to such a situation. So we will reach to a situation when my input string is finished. I am in some state and on the top of push down store 1 is Z0 and on the top of push down store 2 is the Z0 dash. Okay. So in such a situation, what I will do, I will remove these both symbols from the push down store and make both the PDS empty and signal the success. So in this manner, I can match the 4 quantities even with the help of only 2 stacks. Similarly, if suppose I have to match not 4 but the 5 quantities. So suppose an E is also there, E to the power n, it is also there. So at the last, when I was matching D here, so I will be removing A's from here and push A's here. Okay. So whenever up till the second last quantity, I have to make both the operation push and pop. And for the last quantity, I have to do only one operation, that is the popping. So in this manner, I can match any number of quantities with the two-stack PDA. Now I have written the solution of this problem as per the strategy we have just discussed now. Okay. So in the initial situation, when start state is Q0, Z0 is the initial PDS topmost PDS1 topmost symbol, Z0 dash is the topmost symbol or initial push down stored symbol on the PDS2, and in the input we will be getting A. We have to push it over the first PDS and we have to maintain the status of the second PDS. So Q0, and here we have written AZ0 and we have written Z0 dash here, so we have maintained the status here and we have pushed A on the first PDS. Okay, and then in the second transition, now we are in the state Q0, receiving an A in the input. A is on the top of the PDS1 because first A we have already pushed, and on the top of PDS2 will remain same, that is Z0 dash, because we have not pushed anything there. Okay. So now in this situation, we will remain in the Q0 state. In first PDS, we will write AA. So meaning thereby input A has been pushed here. And we will maintain the status of the PDS2. So we have written only Z0 dash here. And now again, third time also, we will be in the situation Q0. On the top of PDS1 is A. And on the top of PDS2 is Z0 dash. So meaning thereby the same situation. So this particular transition will be used multiple number of times and we will push all the A's in our input over the PDS1. So these two transition push A's over the PDS1. Push A's over the PDS1. Okay. Now after it we will start receiving B's. So in the Q0 state we started receiving B's. So first B we have received. On the top of first PDS is A. On the top of second PDS is Z0. In this situation, what we have to do? We have to do a match, and also we have to keep deleted A from the PDS1 over the PDS2 for next matching. Okay. So we have to remove this A. So we'll write null over the PDS1. We have to push A here. So here we will write AZ0 dash. So that's why we have written on the first PDS null. On the second PDS, we have written AZ0 dash. So in this manner, we have matched first B with the A present as the topmost push down stored symbol at the PDS1, and we have pushed this A on the PDS2. Okay. So now A will come on the top of the PDS2, and on the top of PDS1 there will be A if more A's are present there. Okay. So now we have changed to the state Q1. So we are in the Q1 state reading another B. On the top of both the PDS there is an A. Okay. So again, this A we have to remove, and here we have to push. Okay. So from here we have to remove, and here we have to push. So that's why Q1 we will write on the first PDS null, because from PDS1 we have to remove, and we will write double A because here we have to push. So again we will be in the state Q1 reading another B and A on both A and on the top of the both of the PDS. So again the same situation will be there. So again this transition will be used multiple times, and we will match all the B's with the A's present on the PDS1. Okay, and if they are equal in the number, so these two transitions, these push over PDS2 and pop from PDS1. Is it? Now suppose number of A's and number of B's are equal. So all the A's from the PDS1 has been popped. So only Z0, which was the initial push down stored symbol there, it will be present there. And top of the PDS2 will be A's. Okay. So in the Q1 state, we are receiving our first C. Z0 is on the top of the PDS1 and A will be on the top of PDS2. In this situation, now we have to match these C's with the A's present on the PDS2. So we will remove A from the PDS2 and we will push them on the PDS1. Okay. So from here we have to remove, and here we have to push. Okay. So we will change our state Q2 because our operation has changed. So now because here we have to push, so we will write AZ0 here. From here we have to remove, so we'll write null here. Okay. So in this manner, topmost symbol from the PDS2 will be erased and it will be pushed over the PDS1. Okay. So we have done it first time, and then because we are in the Q2 state receiving other C's, and on the top of both the PDS is A. Okay. So now again from the PDS2 we have to remove, and on PDS1 we have to push. So that's why we will write AA here and we will write null here. So we will be in the Q2 state, we will write AA here and we will write null here. Again we are in the Q2 state and on the top of both the PDS is suppose A. So we will again use this transition. So this transition will be used multiple times when till when we match all the C's from the A's over the PDS2. So through these two transitions, we will push over PDS1 and pop from PDS2. Is it? So we'll be doing this. Now we'll reach to a situation, we are in the Q2 state, we are getting first D. Now because we have popped all the A's from the PDS2, now all A's are present on the PDS1. So now we have to do a simple matching because after D we do not have any other quantity to be matched. Okay. So at the PDS1 we will be writing null and we will be writing Z0 dash because we have to maintain its status. So we'll write Z0 dash here and we'll write null here. So we have changed to the state Q3. We have written null here and we have written Z0 dash here. So now we are in the Q3 state receiving other D's. So Q3D on the top of first PDS will be A because we have to match D's with the A's, and Z0 dash on the top of the PDS2. So we have to maintain this up till we do not match all the D's with all the A's. Okay. So now we have written null here because we have to match with the PDS1. So we have written null here and we have written Z0 dash to maintain its status. So if all the D's are matched with all the A's, so meaning thereby on the PDS1 there will be no A. So there will remain only the Z0, which was the initial push down store symbol. And every time because we have maintained Z0 dash on the PDS2, so on the PDS2 will be the Z0 dash. So now we will be in the situation, we are in the state Q3. On the PDS1 there is Z0, on the PDS2 there will be Z0 dash, and because our input has exhausted, because all D's has matched with the all A's, there is nothing left in our input. So we'll take null move, we'll take null from the input and we'll signal the success by deleting both Z0 and Z0 dash from PDS1 and PDS2 respectively. So we'll write null on both the places, on the PDS1 as well as on PDS2. And in this manner we will get our string accepted by empty store. So this was all I wanted to discuss about the two-stack PDA. So now you have understood how we can match multiple quantities or more than two quantities in any number, whether it is 3, 4, 5 or any number. So any number of quantities we can match with the help of two-stack PDA. It is not required that suppose we have to match 5 quantities, so we should have 4 stacks. No, it is not like that. Only with the help of 2 stacks we can match any number of quantities. Thank you all.